Good morning, everyone. Welcome you back for the day 5 on this particular CAN course on hybrid renewable energy system and microgrid. Today, Professor Saad McAlphy is going to deliver on the coordination control of PV and wind farms and microgrid, and also on hybrid renewable microgrid system control and operations. Yeah, thank you one and all joining and handing over to Professor Saad. Yeah, Professor can go.
Okay, thank you very much. Oh, what happened? Yep, I think it's clear now. Yeah, good. So, share the slides. Entire screen. And this. Yeah. Is it clear?
Yeah, it is clear.
Okay, so I think we are at today's the last module, So we will be looking into two main or three main items, which is one is the control and the protections in the microgrid, and then also the energy management will be maybe in the second part of this lecture. Second energy management in microgrids, which are basically related. When you see the control, yeah, and then the energy managements, more or less they are quite related. But we will see some strategies actually, because typically the structure or the architecture of the microgrids is quite standard, in terms of what you call resources utilizations, and for example, we have most of the microgrids will be using renewables such as solar, wind, or hydro, or micro hydro, runoff river hydros, and then we have storage and diesel generators. So typically, this is the structure. There is some new resources which has been introduced in microgrids, which is like the fuel cell system, which also it's relatively new. So in terms of structure, it's quite mature, or there is no much new to add into this structure of microgrid. But there is a lot of work, especially in terms of research. It's on the control part and the energy management part. Even the protection also. The protection, it's very matured also. It's standardized also, matured what you call techniques. So the main focus in terms of research is on the energy management. So the different approaches on the energy management, on different approaches of control of these resources, and especially if you're having what I call two microgrids, peer-to-peer energy sharing, peer-to-peer energy I call sharing between the two, and so on. So these are new, innovative, and what I call techniques that can be used in this research. So let's look into what we are going to discuss today. We will be looking to.
Professor Saad,
Yes, sir.
sorry for the interrupt you. Yeah, today the session is for up to 1 hour only. After that, you will be having half an hour break, and then we'll have another 1 hour session.
Sorry.
Yeah, today, I'll just today the session will be for 1 hour only.
It's 3 hours, right?
Just a minute.
Can you come again, Dr. Siva?
Yeah, I'll tell you that, sir. Today you have a session for half an hour, 1 hour only, sir.
Oh, only 1 hour.
1 hour in the 1 hour in the first half, and then half an hour break, and then you have another 1 hour session.
So total 2 hours.
Yes.
Oh, okay. Okay, good. Thank you. You let me know. Thank you very much.
Yeah.
I thought it's 1.5 hour, 1.5 hour, so it's similar to the previous.
Okay.
So then what we have, I think we have the closing ceremony, right?
Yeah, closing ceremony. Just a minute. I'll also share that if you get some idea of that, how the things are being.
Yeah, please. Yeah.
Yeah. Today, actually, when you have the session.
Oh, yeah.
Yeah, this way, 8:30 to 9:30.
Yep.
And then
10 to 11.
half an hour break, and 10 to 11 one more session. And the participants will be writing the exam from 11 to 12, and then 12 to 12:30 as per the Indian time.
Okay. All right. Okay, good. So yeah. So we need to stop by 11. All right. Okay. All right. Good. Thank you very much for sharing. So I was thinking it's 1.5 hour, 1.5 hour. Same. Doesn't mind. No problems.
Okay.
So we need to maybe. Okay. So let me share again the entire screen. Screen number 1, and then PowerPoints. Yep. And then full screen, and then display, and that's it. I think now it should be working.
Yeah, thanks.
Yep. Yeah, it should be okay. Okay. So what we be looking at, as I said, two focus points for today. One is on the protection, control, and then energy management. So these 3 topics, we will be covering them in today's lecture. So in the first one, we look into how the microgrid. I think this is in terms of control, the requirements, some of the requirements of microgrid. We will be going into more detail between the two main centralized control and this decentralized or distributed, I call centralized and decentralized and distributed control. Then we look into the hierarchical control, these two hierarchical control, okay? And then the architecture, how it looks like, microgrid control modes, then the need for protection, why the protection is important. I think that's very important. And then we look into some challenges in AC microgrid. I think this is here, typo error, is a DC microgrid. Challenges in DC microgrids, different protection schemes for both, because for different, what I call architectures or designs of microgrid, there are different protections requirements, okay? All right, so this is what we're going to look at. So if we look into microgrid evolutions, so what most of the time what we have distribution substations, and then we have feeders, okay? And usually, for example, we have, for example, here circuit breaker here, another circuit breakers, and then we have the loads. These are these are the loads here. Okay, we have the load. This is circuit breakers, and then in each energy source, okay, we will have also circuit breakers. Okay, circuit breakers, and most of these are inverters. Inverters, smart inverters. Smart inverters means, when we see smart inverters, means they have their own control, okay, and able to connect and reconnect and disconnect from the grid. So, and some of them, for example, this energy source is directly connected to the feeder, to the line. So it does not require any inverter. This is maybe an AC source, okay, an AC source. So, and in order for us to control, there is a central, most of the time we have a central control which controls all these circuit breakers. You can see all these circuit breakers are networked and controlled and linked to the distribution substations. And sometimes we also may have what you call an inverter for DC what you call microgrids. Sometimes we may have, if we have, for example, here we have a DC microgrid, then we will have an inverter that's connected to the main feeder. But what you can see from here, is the control structure of the is centralized, and also we also have what we call relay protection. Okay, so that's also its network. So it's evolves. The different requirement, the additional requirements every time that a new requirement is being added. Okay. So the question is always on the microgrid control and decentralized versus centralized. Okay. So, and where is the balance? And what is the what I call the optimum in the combining these factors? If you look into, for example, if we move to 100 decentralized, so microgrid control is complexity is it's an issue. Okay. However, if you look into centralized, so we have a problem of device control complexity. So if you communication requirements and the cost. Okay, so how we are going to communicate between the different microgrids. Okay, so that's actually important. Okay, so latency, this is also issue because an issue between sharing the data and the communication between the two microgrids. Sensors and cost, because we have a lot of sensors and cost that is involved. And then again, the speed and also the reliability, of the issues, because it's decentralized, not centralized control. However, if we have centralized control, then we always look into the performance and the effectiveness, optimum of power flow, okay, the efficiency, the standardizations we need because we have centralized, so the standards that we follow, scalability and modularity, and compatibility. So these are the issues, either centralized and decentralized control systems. So what are the requirements that we look into? For example, there are some fundamental requirements. Is one which is actually very important. It's islanding. Okay, so this is very very important. Means all microgrids should be able to operate on grid connected and islanded mode. So the control strategy that will be developed, it has to be even if it is centralized or decentralized, it has to be able to operate on these two. Okay. Okay. So this is must islanding. Okay. So mode switching with minimum load disruption. So this is when you want to switch from one mode to another mode. Okay. It's very important that we should always ensure that there is a minimum load disruptions, okay, during these transitions. After the transitions, then we look into the stability of the microgrid, stability and how fast you are going to reach to the stability means, and we always measure this with the number of cycles. Okay, for example, within half a cycle, within quarter of cycle, within 2 cycles, within 3 cycles. That's actually give us the speed of these transitions. So for today's microgrids, so we're looking to, for example, decentralized, okay, and in decentralized peer-to-peer. Okay, So here, if you have like I said before, peer-to-peer, this is peer-to-peer energy tradings and peer-to-peer energy sharing and exchange. So this is actually we don't have any master control or communications. So we share the energy between the two what you call neighboring microgrids. For example, like I mentioned before, we have in our university we have two buildings, and these two buildings usually we share the energy between the two buildings. In terms of one building has battery storage, photovoltaic, and wind turbine. Another building, it has the storage, has what you call fuel cell, and also has battery storage. So, and then we try to share the load between the two. And most of this is today's microgrids is a plug and play concept. For example, if I want to add something, I want to add a new storage or add a new generation, so it should be straightforward because it's decentralized and it can be easily transition between the modes. Yeah, so always there is a smooth transition between the modes. Protection, okay. That does not depend on high fault current because it's decentralized. Okay, voltage and frequency stability especially in islanding modes. So most of these microgrids usually has a good voltage stability in this. But future, okay, looking into more complex, okay, we call them layered control architecture device for microgrids. Okay, so we have a device level control and protections, and we have microgrid, level control of so it's limited dependence on microgrid control communications, okay, and looking into more power flow and utilization, especially the renewable energy factor utilization should be as high as possible, and then looking into more standardized. That's actually the key questions and the key. We cannot design microgrids. Every location we design different concept or different control. It has to be standardized and becoming like it's a modular. It would be like a plug and play. It's easy to install, easy to maintain. So that's actually the future microgrids. Microgrids is most of the current microgrids are some sort of like custom design. But what's in the future, we look into microgrid which more modular, more customized, more standardized, and it's a plug and play feature. So there is still evolutions from the today's or the current microgrid structures to new things. Okay, so these are some of the fundamental requirements, and then also we have some other requirements such as the islanding detection and transition. Okay, so islanding detection is very, very important. I think all current inverters, so that's why I call them smart inverters, they are able to detect. Okay, and not only detecting the islanding, detecting the islanding and how fast they can disconnect and then how fast they reconnect back, and transition. So right through comply with the IEEE 1547 in on-grid mode, so the connection to the in-grid mode, and then voltage sag and swell, right through may be required for all the distributed energy resources. So this is for right through. For islanding, as I mentioned just now, there are two types of islanding, either intentional or unintentional or unplanned islanding. So should be able the inverter should be able to detect this. For example, for intentional islandings, okay, we use load shedding, system reconfiguration, device operation mode, and so this is for intentional. Unplanned, so situations awareness and decision making. So this is actually quite important. So for able to, because sometimes it's a plan. Maybe we're planning for maintenance or what you call upgrade or whatever. So that is intentional, but also we have an intentional or unplanned that is due to maybe to fault in the networks. The transition, okay, the on-grid to islanding, okay, that these transitions have to be managed well. Load demand sharing, okay, because moving from on-grid to islanding. So the grid is being removed, so you have a problem of control of frequency and voltage. So it has to be within what you call acceptable margins. And again, from islanding to grid, okay, then we have to worry about resynchronizations and the reconnections device. And in both cases, either on-grid to islanding or islanding to on-grid, we need to make sure it is done within acceptable, time frame. Time. We're talking about one to two cycles, not more than that. And when I say 1 to 2 cycle, I'm talking about one cycle is 20 milliseconds for 50 hertz or 20 or 40 milliseconds as a maximum. So which has to be fast. Okay. And then the stabilizations during the I call this disruption or reduce the disruption level. Okay, so these are the two main few requirements actually for grids. And then now let's look into the what you call the difference between centralized controllers and decentralized controllers. So if we look into the centralized controllers, okay, or we call it MGCC, is the second. It's like here you can see here. Let me put this one here. So this is the centralized controllers here. Okay, microgrid centralized controllers, and it collects information from the load, from the production capacity of the DG unit, state of charge of the batteries, solar irradiance, wind speed, and then run optimization algorithm to determine the optimal operations based on the chosen objective. Like I said before, it's always depends on the objectives. Okay, sending the required setting to the DGs and the storage unit according to the load demand. So what you can see here, we have different what you call. So it's like see here, it can be either it's an AC or a DC microgrid. It's both. It's possible. Okay. And we have different DGs here, different DGs. We have a load. We have circuit breakers. Load. So this information have to be connected and optimization algorithms. It has to be run in order to control. And then you can see here we have even the utility here is connected. So information. So the central controller. Okay, make the decisions based on the resources availability. For example, like we mentioned, the state of charge of batteries. So, for example, we have limits to how much we can charge, we can discharge the batteries. So, for example, the state of charge is 20%. So we cannot discharge it further. But sometimes, if we have critical loads, we may able to discharge further. So this have to be coordinated inside the master control. And also, for example, there is no wind or there is a lot of solar availability. So we can maybe share the power from these DGs rather than what you call utilize, for example, from the grid or from the storage. Okay, so this is centralized. The second one, which is the decentralized, okay, decentralized structure, which is here the DGs, inverters, and loads are controlled individually by local controllers, and those controllers interact and communicate among each other. So what does this mean here? We have local controllers in each unit. Local controllers, each one having a local controller. Okay, all right, and then we have these DGs here. And you may have what you call connections, or what you call to the main bus or to the main systems, okay, and decisions are taken locally, okay, and maybe the negotiation can take place as the different actors as usually have different goals, for example, the local controllers, so we have a communication link which links to the main system, okay, and then we have the what we call the local controllers, and then we have here the CMG, the main the controllers that shares. But the decision here all is based on each unit. So the big challenge is the communication among the others. So we need the communication need to be shared. For example, how much active power will be contributed by this DG, and then how much active power from here, and then reactive power, for example, or frequency contribution to frequency I call regulation, and so on. So each one have advantages and disadvantages. This looks quite straightforward. Okay, so you depend on the local controllers of each unit. Okay, and so let's maybe summarize the advantages and the disadvantages of centralized centralized controllers, and then we look into this. For example, if you look into the main advantages of centralized controllers, can provide a high operation knowledge because you are aware of all what's happening, so the main goals are clearly identified and achieved. Okay, so that's the good things. They can provide a global optimal solution. Global optimal solution means by looking into the global means here the global means not the word, talking about the global means the global microgrid system. Okay, so because it's connected to the grid, it's connected to all the devices and to the loads, so we are aware actually what's happening at each part of the systems. Also, this enables easy synchronizations to the main grid because we know all the available sources and loads, and then also the grid, and then they can use real-time signals for online operations. So, okay, it is preferable for the interconnections to several microgrid systems, okay, and setting large-scale energy markets for energy trading. So the good things about this is it's preferable for setting large-scale energy markets. Yeah, I think in terms of standardizations and what I call standardizations, procedures very quite easy to implement because we have one central control unit. But however, there are some disadvantages of this central controllers for microgrids. This one is the high communication requirements. Okay, so because you have to have connections from all the circuit breakers, from all the DGs, from all the all these have to be connected. So sometimes in terms of location, physical location, they are maybe apart. So there is a lot of cabling and I call wiring requirements. Okay, and also because such a large amount of information and data, so in terms of computational burden, okay, computational burden is quite high and it's time consuming. So that's actually one, because you are not dealing with one source until you might have multiple resources, and each resources have different data, different input. So this can be computational intensive, and that may lead to what I call to delays and sometimes making decisions, whatever. So these are the advantages and disadvantages of what you call centralized controllers. Also, decentralized controllers also has something to offer. If you look into the decentralized controllers, also they have some advantages and some disadvantages. For example, if you look into the advantages of decentralized controllers, so it's properly preferred control, especially for the owners of microgrids. Okay, several decisions are taken locally by the intelligent controllers rather than accepting set point detected by centralized controllers. So here, the central controller does not give any decisions, but everything is done locally at each what you call source. So it's fast changing. Okay, they are suitable for fast changing infrastructures. Okay, so because you just remove one or you add one, so it's very, very straightforward compared to these centralized controllers. Easily expanded. Okay, because they have the plug and play capability. So if you have a building and a microgrid, which is you have a future plan to extend, or maybe your load will increase in the future, then I think decentralized controllers will be the best options. Because if you use centralized controllers, so there are a lot of other additional wiring and additional communication links have to be established. It's quite, they have a very high reliability. Okay. So because the failure, it happens in one, then doesn't affect the rest. Okay. So that's a good things. However, they have some disadvantages. Okay. One of the disadvantages is quite complex, especially with multi-ownership and competitions between various actors or agents. And this is due to the fact that each agent seeks to achieve its own objective, such as maximizing its profits. So this is the hidden part, because so you have a local control. Everyone, for example, everyone at home, for example, want to inject the maximum power to the grid because they want to make more profits. But if you have centralized control, these are optimized locally in one central controllers. But here you have that what you call the absence of this control or this feature. Okay. So sometimes we even ignore the instructions or the communication between the DGs. So like I say, it's there is no perfect or solutions that's actually for one, but it's always trade-offs. Okay, and as I said just now, it depends on the objective of designing this microgrid. So the objective have to be very clear, and what is the main objectives, and then based on that objectives, then the right control strategy have to be selected to meet the objectives, because there is no one control that can fulfill all the objectives. Okay, so we have these two, which is quite clear, centralized and decentralized. So now let's look into another control strategy, which is, we call it distributed. Okay, so distributed. So what does means distributed what we call control? Distributed control is a non-centralized control scheme. Okay, it is similar to the decentralized, except distributed control techniques do consider the interaction among the DGs. So that is the main points for distributed. If you look into the decentralized, you can see here clearly here mentions that ignores the interaction between the DGs. So to solve this problem, okay, a new control techniques for microgrids is proposed, which is similar to distributed, but there is interaction between the microgrids. And what you can see here, and it does not require what you call additional or dedicated communication networks. Okay, and centralized controller to coordinate the DG's units in microgrid. So what you can see here, we have the, this is the bucket grid, and then we have the DARs here connected, and then we have the controllers. Each DAR have its own controllers, but these own controllers actually communicate with each other. So there is an interaction between the controllers. So this is what you call the cyber layer, and this is the microgrid. So the DG's units have autonomous local control because each one have their own controllers. You see, each DG has its own autonomous controller, and there is active communications among them because, like you see here, the active communication that is ensured by each DG over the networks. Okay, and also it allows plug and play, so you can add and then you just can control the main units, and it's provide a better flexibility, and also it's better than in terms of firm performance. It's over the centralized and decentralized controller. So it's something, it's like in between. If you ask me what does this mean, it's something is in between. So now let's put the three control techniques together. If we put the three control techniques together and try to compare them, how they look like, So if we put them together, they will look something like this. Okay. All right. So if you look into decentralized controllers, you can see, like we said before, we have the DG, we have the local control units, and then we have this is the physical I call connection bus. If you have centralized, so you have the DGs, you have the local control, and then you have the microgrid central controller. Yes. Okay. If for distributed, okay, so it is looks similar, but here we don't have the master control, but we have the instruction and the communication between the local DGs. Okay, so that actually summarizes the three what you call control techniques that actually used in microgrid. So once, if you design your microgrid, so you have one of the three options that you can use, and this is have to be designed or have to be selected at the planning stage. A planning stage means at the beginning when you want to setting the objectives. Okay, which are the best? Am I going to go for decentralized or centralized or distributed control techniques? All right. So I hope that's now we are clear on these control techniques. Next, we will move into a hierarchical control, which actually we have mentioned before about it. Okay, but if you look into, for example, the distributed control and the control hierarchy are too closely related. Okay, so if any systems with sufficiently high number of units, one way to provide the coordination strategy is to employ control hierarchy, and that's control hierarchy actually helped us. I think we already discussed this before. We have this hierarchy, which is the primary control, secondary, and the tertiary control, and the dynamic response is increases as we go lower, and each control will in charge of or responsible of something, So, for example, if you look into primary control, voltage and current control, drop control, which we will see later. Okay, virtual impedance. Secondary control is restore frequency and voltage, power sharing, accuracy, voltage quality enhancements, optimal power flow and economic dispatch. So I think we have explained this before. If you look into in the actual system, this is how it looks like. Okay, so we have the primary control here. So you can see the PQ drop control, reference generators, and then we have the inner control loops, and then we have the measured voltage and measured current, and then we have the modulators, and then we control the switches, and then the microgrid source. And secondary levels, which in charge of voltage restoration loop and frequency restoration, frequency restorations. And then the tertiary core is more into economic, okay? So how much active power and reactive power, controlled, okay? And how much we sell to the grid and how much we absorb, okay? So I think we also seen a number of slides on this topics previously. So this is just a summary. I think we already mentioned it's, for example, looking to the primary control is also known as the local internal control, secondary, which is the central control of energy management system, and the tertiary control is the highest level of control, which send the long-term points, in terms of DARs, market signals, system requirements, and also managing multiple microgrid and its parts of the host grid. So managing some different control. Okay, so let's look into now the microgrid control architecture. So in microgrid control architectures, okay, microgrid has two different modes. I think all of us know. I think all of you should know. We have grid connected, and also we have islanded mode. These are the two modes, okay? Or we call it grid disconnect mode. So these are the two modes of operation. And microgrid should be able to operate reliably in both modes. So either it is a grid connected when the grid is supporting, or without the grid, it should be reliable. When I say reliably here, we are referring to, excuse me, we are referring to the quality of voltage and frequency that is what we call produced by this microgrid. Okay, and depending on the role of distributed generations in the microgrids, okay, the control architecture can be divided into following. We have one master-slave control and peer-to-peer control. Okay, master-slave. So there is one is a master, another one is a slave, or it is peer-to-peer communication. So let's look into the first one, which is master-slave. Okay, so in master-slave operate in islanded mode. Either the DG or the energy storage systems of the master unit will take voltage frequency control role to provide the voltage and the frequency for other DGs, and they assess within the microgrid. Okay. Meanwhile, other DGs are in PQ control mode. Okay. If you look like here, if you look into here, so this is the master, okay, which will be in charge of frequency, voltage, provide voltage and frequency reference for the other DGs and the AS within the microgrid. So this is the we call it the master. This is the master here, okay, and the controller, okay, for the rest, okay, you can see here is the PQ control, which is the slave. Okay, so means there is one master controller, and then we have the slave controllers. So and the slave controllers take corresponding actions based on those master controllers. So we have the power electronic interface, we have the master unit, which is the battery storage system. Okay, so based on that, he generates the reference and voltage and frequency, and the rest will be done by the PQ, will be done by the sleeve controllers. So this is just an explanation. So how it works, the master sleeve control. Okay. For example, if microgrid operates in a grid connected mode, in most situations where the main grid provide the voltage and the frequency references. So if we're having a grid is connected, okay, and then actually there is less problem or less issue because the grid provide the reference voltage and frequency. So all the controls within the microgrids are in a PQ control mode or in the slave mode. Okay, but in case if fault happens, okay, on the main grid, okay, and then the main grid can transfer to the islanded mode. One of the DG's controllers, which is the master, need to switch to voltage and frequency control. So this is what happened actually. Okay, so if grid connected mode, we have no issue because the grid is the reference. Okay, and that's actually, and all the remaining microgrid, operate on slave mode or PQ mode. But if it is disconnected, the grid is disconnected, or is due to the fault or due to whatever, okay, so it has to operate on one of the units in the microgrid have to be to operate and on the VF control mode. And which is the most commonly used what you call master units that can be divided into three. So we have the energy storage system, we have the DG, okay, and diesel generators, and then we have the also DG integrated with the DG. So if the AS is used as a master controller, the microgrid cannot operate in islanded mode for a very long time. So that's the issue, okay? Because the discharge of the batteries, okay, will prevent from voltage and frequency regulations. So that's actually an issue. But if we have a diesel generators or another DG, like micro turbine, or is used as a master, the voltage and frequency can be regulated easily, okay, and can operate in island mode for a long time. So these are the options. However, if you ask me in terms of response, the ASS is faster in terms of response compared to another micro turbine. Okay, and so this is the trade-offs that need to be taken. Okay, also there is another. So this either we use the ESS, okay, or we use the DG. So this is the two options, and this is the we call the disadvantage of each one. Okay. Another method is to use the DG and the ASS as a master together. Okay, so this is another option. So here we rely less on the DG. Okay. This method works for renewables. Okay, renewable generators, PV, wind, turbine, and so on. Okay, but due to the intermittence and the nature of these renewables, DS can help reduce the voltage and the frequency fluctuations. So here the ASS is not the main, but it's just supporting in case there is the fluctuations in these DGs, or distributed generations. Can be a diesel, can be a PV, can be a wind, but the nature of this, it's we call intermittent in nature. So the ASS can only help reducing the voltage fluctuations, in microgrid. So I hope it's clear now. The master sleeve controller. So in the master sleeve control, okay, so we have two. One is the PQ control and the VF control. Okay, VF control usually is in charge of one of the masters, either the battery energy storage systems or any other DGs, or it can be a combination of both. Once this one is operated on island mode, but if it is grid connected, so the grid is the master, and all the rest will be operating on a PQ controller. All right. All right. So this is the master slave. So now look into peer-to-peer. Okay. Okay. Peer-to-peer. This is actually also a very hot topic in research. Okay. Quite many, actually, I have seen quite a number of papers recently published on this, on peer-to-peer control. Okay, for peer-to-peer control of an islanded microgrid, all the DGs and the AIS units are equal with no master-slave relationship involved. So what does it mean? Means everyone is responsible in maintaining the voltage and frequency, and also P and the Q control. Okay. So using the troop control methods, designated to DGs and the energy storage system units are capable of adjusting their power outputs based on the locally measured voltage and frequency. So local voltage measured frequency, and based on that, each DG have to act. So you can see here we have here we have the VF control measure, we have the local loads, okay, and each unit or each things, you have the drop control one, we have the power electrons, we have the storage, and then we have the frequency and the voltage, for DG1, DG2 till DGN, okay, and we have the electric connections between peer-to-peer. That is different resources, and then we have one maybe this peer-to-peer supports, to help monitor. But the energy is shared between the two, and we have data uplink, and then we have also active exchange agreements. There is an agreement, that being shared and being. And in any large change in load, sometimes there is one overloaded, can be actively shared among the selected DGs and also the energy storage systems, okay, based on individual drop coefficients, so that the power balance between generations and the consumption is re-established or maintained in islanded operations. Okay, so in case there is an islanded operation, so what happened here? The power will be shared between this peer-to-peer. We call it peer-to-peer power sharing. So, and in peer-to-peer control, okay, belongs to error frequency regulations. So that allows some frequency and voltage deviations. Okay, so we expect some deviation, especially if it is in islanded mode. And compared to the previous one, which is the master-slave control, peer-to-peer control enables each DG and the battery storage systems to automatically participate in the power output allocations, which facilitates the plug-and-play functions. Okay, so this is the main advantage of the peer-to-peer. So it's allow plug-and-play what you call functions, okay, compared to the master and slave. And also the peer-to-peer control, okay, what you call the communication, the control communication systems, can be avoided, and can what you call the cost can be quite cheaper, in terms of implementation. So these are the the pros and cons of each of the master slave and what you call peer-to-peer control. Okay, now let's move into what you call oh, we have another 2 minutes. Microgrid control methods, where we I hope it's clear, so we start with the centralized, decentralized, and then distributed, and then we look into the master, what I call master slave. We look into the architecture. I think this is we have discussed before the architecture, and then we look into the what I call the master slave control techniques, and then now we look into the microgrid control methods. So I'm not sure. Maybe it's another 2 minutes to, or already 1 minute to. If any questions, maybe you open for questions. We have 1 or 2 minutes for questions, and then maybe in the next we will be looking to the PQ control, the VF control, and the drop control.
Any questions from the participants?
Yep.
You can unmute and ask the questions.
Yeah, please. You can ask directly, or you can even let me put this one here. Stop sharing. Maybe look into the chat box in case there is any messages or any comments. No. Hello, guys. Any questions or comments or whatever?
Sir, good morning. Sir, can you provide some resource where we can see these microgrid control these in action? For example, if you can give some examples in MATLAB where we will see the implementation of these control techniques.
Okay. All right. I will give you some resources where you can. The best one is the. I will share with you some, because some of these are extracted from papers. Some papers which has the models. And most of them they use either PSCAD or sometimes they use MATLAB, to simulate these control techniques. Okay, maybe I will share with Dr. Shiva some of these resources, Okay, there is a question here.
I have one question, President.
Yeah. Sorry?
I have one question.
Yeah, please.
Yeah, when you're operating the inverter in the group control, just take the frequency and voltage, then in that case your DG is floating to deliver the power, or it also have the restriction of what is the load on the respective renewable energies.
Sorry. Can you? I didn't.
When you're operating at the voltage and frequency control.
Yeah, voltage and frequency control. Okay.
How will be the restriction on the power delivered to the grid, the microgrid?
Yeah, because in the what you call in the control, like I said just now, there are two objectives. Okay, or two things that we need to maintain. One is the voltage and frequency control, and then the PQ control, right? I'm not sure if I understand the question.
No. See, when you're operating at the voltage and frequency control,
okay,
your distributed generation or the renewable energy source is operating to maintain the voltage and frequency.
Depends. It depends. It depends. If, like we said just now, is it what you call master slave or peer-to-peer?
Okay.
So if it is in a master slave, means there is, for example, the energy storage system. Okay, if the energy storage system is the one used to maintain the frequency, also depends on which mode you are operating, on islanded mode or on
islanded
mode.
On islanded.
Yeah, if it is on islanded mode, so part of the microgrid have to take responsibility on the voltage and frequency control. Most of the time, it's maybe the energy storage systems, or maybe energy storage system in combined with one of the DGs. Okay, so it can be a DG, but a DG because it's intermittent, especially if it is changing, very fast. So, and if it cannot be also a battery, because the battery also it can run out. So it has to be something which can provide the stability of the voltage and cannot be what you call can sustain at least a certain level of stability in the voltage and the frequency. We will discuss maybe in the next on the drop control later.
Yeah. methane.
Okay. And then I think